Now we move to the topic for the molecular term symbols with single electron in the orbital. For a linear molecule, it lost the symmetry which is same to the atomic orbital. For the atoms, electrons are categorized by their total orbital angular momentum L. However, in linear molecule, the spherical symmetry is lost, but it still retains some symmetry, which is the cylindrical symmetry along their bond between the two atoms. So, the state of the electron in a molecule still can be quantified using the angular momentum along the bond between the two atoms, or given the symbol of Lz. Therefore, we use the molecular angular momentum quantum number around the internuclear axis to label the state for the electron in the molecular orbital. Lambda state, or the Lz value for the linear molecule of an electron in a molecule, is designated using this small Greek letter. So lambda equivalent to the value of Lz. So the Lz value could be 0 or plus minus 1. For the formations of the sigma orbital, it is correspond to the lambda equals to 0, while for pi orbital corresponds to lambda equals to 1. As an example, a p orbital has L equals to 1 and it possesses Lz equals to 0, plus 1 and minus 1, which translate into this molecular designation. Atomic orbitals combine to form molecular orbitals. For sigma bonding, Pz, or lambda equivalent to Lz equals to 0, combine to yield the sigma molecular orbital and also the anti-bonding molecular orbital, or we call it as the sigma star. Conversely, the pi bonding that involve the px or py orbitals, where the lambda is equivalent to the Lz equals to either plus 1 or minus 1. This orbital will combine to produce the pi bonding molecular orbital and also the pi anti-bonding molecular orbitals. It is important to note that there is no lambda equals to 0 for the pi molecular orbital, because that specific orientation, which is this one, is strictly associated with the sigma molecular orbital. When moving from a single electron to a system with several electrons, we use Greek uppercase letter lambda to represent the total orbital angular momentum around the internuclear axis. This total value is the sum of the individual angular momentum. So you have the capital letter lambda equals to the lambda 1 for electron 1 in the molecule plus the lambda 2 for electron 2 in the molecule, and so on. These states are assigned specific symbol. For lambda equals to 0, the symbol given is sigma. For lambda equals to 1, then the symbol given is pi. If the total orbital angular momentum of the electrons around the internuclear axis is 2, then we use this triangle to represent the state for the lambda, and so on. The total spin quantum number S is determined by the combinations of individual spin for each of the electron in the molecule. The possible values for spin quantum number range from the sum of the spins down to the absolute difference, typically separate by 1 unit. So you can find out the maximum value of the spin quantum number and then minimum value of the spin quantum number. and then fill in the gap in between this maximum and minimum value, whereby they different by 1 unit until they achieve the minimum value. So from this, we calculate the multiplicity of the molecular state using the formula 2s plus 1. The axial component of the total electronic angular momentum for a molecule. In this system here, the spin-orbit coupling is responsible for lifting the degeneracy of the electronic states. This occurs because the z component of the spin interact with the z component of the angular momentum come from this orbital. So this interaction generates a total electronic angular momentum along the z-axis or the molecule axis, which is denoted with the symbol of Jz. The z component of the total electronic angular momentum is represented by the symbol of omega, which is the sum of the z component of the spin given the symbol of italic sigma and the orbital angular momentum given by the symbol of capital lambda. Here, the sigma refers to the italic capital Greek sigma, representing the axial component of the spin with possible value ranging from s to minus s. So do not confuse this sigma with the state symbols, which is the capital letter sigma for the orbital angular momentum quantum number for along the z-axis for the molecular orbital. While the absolute value for this total electronic angular momentum with reference to the z component, which is the omega here, is attached to the molecular term symbols as a right subscript to distinguish between the different energy levels. Similar to the atomic term symbols, the linear molecule, where the molecular term symbols, it has the same format with the superscript represent the multiplicity. Then we have the state symbols. After that, we have the subscript, which is the result of the spin-orbit coupling effect. The only difference is that for the molecular term symbols, where the molecule is linear, the angular momentum used in determinations of these state symbols is according to the angular momentum with reference to the z-axis or their internuclear axis. In addition to these three parameters, which is the multiplicity, the state symbols, and also the effect of spin-orbit coupling, they have other parameters such as parity to label the molecular term symbols. Parity is applied for homonuclear diatomic molecules, where they consider any point in the molecule and note the sign of the orbital upon the process of traveling on a straight line through the center of the molecule to a point at the same distance on the other side. So if the wave function remain unchanged after the process of inversion, then we call that as the parity with G or symmetric. If the wave functions after the process of inversion change, then we call that parity as ungenerate or antisymmetry. So this is what happened in the sigma molecular orbital. You just choose any point within the molecular orbital. After that, conduct the process of inversion. So they travel a distance through the center of inversion and then to the other end with the same distance from this point to this point and from this point to this point here. If the wave functions sign after the process of inversion are the same, then we call the parity as Gerard or symmetry. So for the sigma bonding molecular orbiter, after the process of inversion, the sign of the wave function remain the same, so positive and positive. So we say that sigma bonding is with the parity of Gerard, while for the sigma antibonding, after the process of inversion, the wave function sign will be changed from positive to negative. Therefore, sigma antibonding molecular orbiter is categorized as the parity with antisymmetry or ungerad with the symbol of U. While for the pi bonding, for the pi molecular orbiter, after the process of the inversion, then we will observe that the wave functions will be changed after the inversion. So we call the pi bonding as the ungerad parity. While for the pi antibonding, this molecular orbiter remain the same wave functions after the process of inversion. So pi antibonding is with the parity of symmetry, or we call it as the Gerard. Therefore, in summary, bonding sigma orbitals and anti-bonding pi orbitals are always symmetry in the inversion, while the anti-bonding sigma and also the bonding pi molecular orbitals are always ungerad or the antisymmetry after the process of inversion. To find the overall parity of a state with several electrons, you multiply the parity of each individual open shell electron, meaning that the non-fully filled orbitals. The rules follow a simple logic, where if electron 1 is in G orbital, electron 2 also in the G orbital or the Gerard orbital, then the overall parity will be G. Similar to if electron 1 in the U orbital, the other electron also in the U type of molecular orbital, then the overall parity is also G. But if one of the electron in U and the other one in the G molecular orbital, then the overall parity will be U. So these rules are generated by interpreting that if you assume G is +1 and U is -1. So +1 multiply +1, you will get the overall equals to +1. +1 multiply -1, then you will get the overall as -1. For example, what is the parity for the state for these molecular configurations? If you have 2 electrons in the sigma bonding, 2 electrons in the sigma antibonding, 2 electrons in the 2s or the 2 sigma bonding, and 2 electrons in the formations of antibonding. And lastly, you have 1 electron in the pi bonding, another electron also in the pi bonding. We only consider the parity for these 2 electrons in the open shell. So both of these electrons are occupying the pi molecular orbiter. It has the parity of U. So U multiply U, you will get G. Therefore, the parity for the overall configurations is G. Another symmetry element is the reflection through a plane that contain the internuclear axis. This reflection property only applies to sigma state, and the sigma state are labeled as sigma positive or sigma negative. The sigma positive represent the no change in the reflections, just like the image shown here. We have the mirror plane placed through the internuclear axis, and through the process of reflections, there is no change in the wave functions. So it is labeled as sigma plus. For the reflections that results in the change of wave functions, then it will be given the symbol of sigma minus. For other states like pi, delta, phi, both symmetry types exist simultaneously. By analogy with atom, we use a specific format for the molecular term symbols, which is limited to linear molecule. So this is the standard format with superscript 2s plus 1 for multiplicity. Lambda is the state symbols. When lambda is equals to 0, it will be given the symbol of sigma. When lambda equals to 1, then the symbol is pi. When lambda equals to 2, then the symbol is delta. Next is the subscript. The subscript is due to the effect of spin-orbit coupling. So the omega is referring to the coupling of the spin and the orbital angular momentum in the linear molecule, which is reference to their internuclear axis. We have the orbital angular momentum quantum number with reference to the internuclear axis plus the spin of the electron with reference to the internuclear axis. Therefore, this is the molecular term symbols for a linear molecule. Here we look at two examples. The symbols 3 triplet pi u indicates a spin of 1, a total orbital angular momentum lambda equals to 1, and a wave function that changes sign upon inversion, so it has the symbol of u ungerad. While the symbol for singlet sigma plus indicates a spin of 0 and the lambda equals to 0. So it has the state symbol of sigma and a wave function that remains unchanged upon reflection. Therefore, it has the symbol of plus here. And we have to take one more note is that this is a heteronuclear molecule. The G and U subscript are not used in this molecular term symbol. Let's apply these concepts to hydrogen molecule, which has the configurations of 1 sigma G 2. So we have the atomic orbital for hydrogen, and molecular orbital for the hydrogen molecule. So basically, all the electrons are pair. Therefore, the number of spin up of the electron is same as the number of spin down of the electron. So the total spin quantum number with reference to the internuclear axis, so this is the italic sigma, or equivalent to the Sz, equals to the spin up plus the spin down. Sz plus 1 over 2, Sz minus 1 over 2, it is equals to 0. Therefore, the spin quantum number is equals to 0. If S equals to 0, then the multiplicity will be equals to 1. Then next we have to find out what is the angular momentum quantum number around the internuclear axis. Because both electrons are in the sigma orbital, therefore lambda 1 or the angular momentum quantum number for electron 1 with reference to the z-axis or the internuclear axis is same as the lambda 2. So both are in the same molecular orbital. And because this molecular orbital is in the formations of the sigma bonding, so it has the value of 0. Therefore, the capital lambda, which is come from lambda 1 plus lambda 2, is equals to 0 for the molecules. So when lambda equals to 0, then the state symbols is sigma. Next, we have to find out what is the spin-orbit coupling effect along the internuclear axis, omega. lambda equals to 0, italic sigma also equals to 0. Therefore, the omega is equals to 0. Because this is a homonuclear, therefore it has the parity of the symmetry, which is hydrogen has a inversion symmetry and electron 1 is in the g orbital. Electron 2 is also in the Gerard orbital in the formation of the sigma bonding. Therefore, the overall parity for the hydrogen molecule is G. We can write the molecular term symbols for the hydrogen molecule as singlet sigma G. Continue with the boron ion. The electron configuration is given here. So you have 2 electrons in the formations of 1s orbital and then 2 electrons in the formations of the sigma anti-bonding molecular orbital. After that, 2 electrons in the sigma bonding molecular orbital, 2 electrons in the sigma anti-bonding molecular orbital. After that, it has only 1 electron in the formations of pi bonding molecular orbital. We only consider the last part here of the configurations, which is the open shell. So only 2 pi 1. This 1 electron contributes to the determinations of the molecular term symbols. The total spin angular momentum quantum number S is equals to 1 over 2 because we have only 1 electron. Therefore, the multiplicity equals to 2 times 1 over 2 plus 1 equals to 2, which will give rise to a doublet. And since the electron is in the pi molecular orbital, so the orbital angular momentum quantum number around the internuclear axis is either plus 1 or minus 1. The total molecular orbital angular momentum is therefore lambda equals to plus 1 or minus 1. And this is corresponding to the pi state. So we have a term of doublet pi. Since the electron that contributes to the term symbol is in a 1 sigma pi u molecular orbital, then the parity is ungerad. Therefore, the complete molecular term symbols for boron ion is doublet pi u because it is a homonuclear diatomic molecule. So we can also include the parity in the labeling of the molecular term symbols. Consider an excited state with the configurations of 1 electron in sigma g orbital and 1 electron in the pi u orbital. Here, there are 2 electrons involved. So the total spin quantum number can be either 0 or 1. So in this case here, electron 1 spin quantum number is 1 over 2. Electron 2 spin quantum number is also 1 over 2. So the maximum value is 1 over 2 plus 1 over 2. Then you get 1. Then the minimum value is 1 over 2 minus 1 over 2. So you will get 0. And this leads to a singlet and also the triplet multiplicity after you substitute the value of 0 as well as the 1 into the multiplicity determinations. So you have 2s plus 1 equals to 1 or 3. The molecular orbital angular momentum quantum number with reference to the internuclear axis for electron 1 and electron 2 can be determined where for electron 1 it is labeled with lambda 1 because the electron is in the sigma bonding, so it has the lambda 1 equals to 0. While for the electron 2, it is involved in the formations of pi bonding. Therefore, lambda 2 can be the value of either plus 1 or minus 1. And the total molecular orbital angular momentum quantum number, considering the combinations of lambda 1 equals to 0 and lambda 2 equals to minus 1, therefore, this capital lambda has the value of minus 1. If we consider the combinations of lambda 1 equals to 0, while lambda 2 equals to plus 1, then the capital lambda will have the value of plus 1. So all these combinations, it to the value of lambda capital equals to either plus or minus 1, which is corresponding to the pi state as the state symbol. Now we have determined the multiplicity and also the state symbols. So we have the possible term symbols for this molecule is triplet pi and also the singlet pi. The parity of this state. The overall parity is therefore G times U equals to U because one electron is in the sigma bonding molecular orbital. Another electron is in the pi bonding molecular orbital. So it has the parity of G for electron 1 and U for electron 2. Therefore, the overall parity is U. And the complete molecular term symbols are triplet pi U and singlet pi U. The energy ordering. The Hund's rule serves as a guide for the energy ordering of the molecular term symbols. First, the term with the highest multiplicity is the lowest in energy. Second, for term with the same multiplicity, the one with the largest orbital angular momentum, lambda, is the lowest in energy. For example, the terms for oxygen lies in the order of triplet sigma, followed by singlet delta, followed by singlet sigma. So the one with the highest multiplicity will be the lowest in the energy. If they have the same multiplicity, then we have to check for the state symbols. The state symbol is corresponding to the orbital angular momentum quantum number with reference to their internuclear bond axis. So the value which is the largest of the orbital angular momentum quantum number, then it will be lower in the energy. Therefore, the sequence is this one is the lowest in the energy, followed by this term, and then this term has the highest energy. These states are all arises from the lowest electronic configurations for the two electrons which are present in the pi antibonding molecular orbital for the oxygen molecule. So each of these electronic states of a diatomic molecule, there is a potential energy curve. Each of these curves is represented by one of the molecular term symbols. Just now we have already arranged the ordering of the energy for each of these term symbols. So the one which has the lowest energy is the triplet sigma G, followed by singlet delta G, and then the singlet sigma G has the highest energy. When we talk about electronic transitions, it is actually involve the transitions between the state from one state change to another state and not the orbital. So the change of the state, for example, in this molecular term symbol, the electrons are arranged in this manner in the molecular orbital. Upon the excitations, the molecule will be excited or the electron will be excited upon activations by the light source. So it will be changed from one potential energy curve to another potential energy curve, or we say that the energy will be transferred from the light source to the molecule and cause the activations of the electron to change the state from this potential energy curve from this energy to higher energy level. So that change the arrangement of the electron, which results in the difference in the state. So electronic transitions occur between the states and not the orbital.